So here are representations of the carboxylic acid family derivatives. There's a dividing line in the sand that pretty much runs between the anhydride and the ester. So starting from the top, we need to be able to name these. We need to be able to draw these on an exam. Okay? We have an acyl chloride, very top, right? Should be the only one with a Cl in it. The next up is the anhydride. I recognize it as an anhydride because it's a central oxygen flanked by two carbonyls. There's a carbonyl on either side, right? That's an anhydride. Okay? The third one down, that central oxygen is flanked by a carbonyl and an R group, right? That's different than the anhydride above. This guy's an ester, and we end with an amide. I remind you that this amide, this nitrogen of the amide, can have two R groups off of it, can have two hydrogens off of it, it can have one R group and one hydrogen. We're going to learn how to deal with that, but that's generally, any of those are considered an anhydride. I mean, not an anhydride, pardon, an amide. Okay? The central line in the sand really comes as a turning point. The acyl chloride and the anhydride are reactive enough to react without a catalyst. We have two types of catalysts. We have acid catalyst and we have base catalyst. Regardless, we don't need a catalyst for an acyl chloride or an anhydride. It's not a necessity. You generally do not see it. Below, we have catalysts. We have acid and base catalysts that are necessary in order to run these reactions. Okay? That's a big difference between the top two members and the bottom two members. Okay? We're going to be playing that out with workshops because we teach this unit a little bit differently than I teach other units. I'm not going to be lecturing at you for days on end about all of this stuff. Starting on Wednesday, we come in with workshops and we literally sit and work on them in groups, and I talk about some of the problems you guys are having, some of the things I know in general people have, and then some of your specific problems, but you leave with almost 10 or 15 problems. You've worked on some of them in this room. You have the remainder for discussion or to work on in small groups. The answers are handed out immediately, so you have the answers as well. So we work in workshops for these two units that are coming up. So that should help us as we move forward because there's tons of problems and they're exactly like the ones you're going to see on your exam, right? So that's very helpful. You need to get through those workshops, okay? All right. Each one of these is considered a derivative because on hydrolysis, what's hydrolysis again? Adding H2O. Okay, on hydrolysis, they all give me back the parent carboxylic acid. They all give me back the parent carboxylic acid. Okay? So, I can tell you that this here is a reflection of the R group of the parent carboxylic acid of that acyl chloride. Right? If I think that I'm going to take this and get back the parent carboxylic acid, that carbonyl carbon and anything on the R group side all stays the same. I'm only swapping out the Cl for what makes it a carboxylic acid, and that's the OH. Okay? So its parent carboxylic acid is this here, where the Cl has been swapped out for an OH. I would name this parent carboxylic acid acetic acid. This is one of those common name ones. It's also known as ethanoic acid, so you can call it ethanoic acid. But to be quite honest, even though that's an IUPAC name, technically, it's generally known as acetic acid. Okay? That's acetic acid. The carboxylic acid is acetic acid. So the question is, what do I name the acyl chloride that hydrolyzes back? Because the first thing I need to do is know how it would be named as a carboxylic acid. The way I name this guy is I take the ic acid and I swap it out for the suffix that we know is required for the acyl chloride, and it's acetyl chloride. So you can say I've switched the ic acid for YL chloride. And sometimes it's OYL. For instance, I look at this guy here, okay, I box out the part, right, that I know is going to stay the same. This part here, right, I swap out the Cl for the OH. That's its hydrolysis, right, back to the parent. So I would name this guy as 2-methyl butane, and this is where I would be oic acid. I'm oeal chloride. Okay? So if you have the O in there or not really going to ding you on it, right? Just saying. Don't be confused that some of them, are missing that O. For some, it's just not acetoyl chloride. I don't quite know why that is. It's probably just something that's happened over the years. Okay? Does everyone understand how to name this creature? Okay. The anhydride will hydrolyze to give me back 2 moles of carboxylic acid. Okay? I can see 2 carbonyls, so I can see that I have 1 mole here. Right? I did exactly what I said. Take the carbonyl and any of the R group with it, and the other mole is here. Okay? So this specifically gives me 2 moles. Every anhydride gives me 2 moles of carboxylic acid when I hydrolyze it. This is an example of an asymmetric anhydride. An asymmetric anhydride. Because I have 2 different R groups, right? So I have an R group over here and on the right that are different, right? This is a 4-carbon chain, this is a 2-carbon chain. So this is what I would say is an asymmetric anhydride. You can also have symmetric anhydrides. So clearly, this is 2 moles of the same carboxylic acid I get back upon hydrolysis. Does everyone understand what I mean by boxing them out and seeing that? Okay. So the symmetric ones are easiest because I would name this acetic. So I keep everything but the acid. I would name this acetic acid, right? Carboxylic acid I get back. But I drop the acid and I just put in the anhydride. So instead of the acid, I get the anhydride. So this is acetic anhydride. Questions about that? When I've mixed anhydrides, I have to have 2 names before. And they're generally alphabetical, but again, no one's going to dig you on that. So it's acetic, and then my little caret to say there's a space. And then butanoic, and then a space, anhydride. So it's acetic, butanoic, anhydride. Okay? That's in essence naming each one of these R groups that I had, right? This would give me 1 mole of butanoic acid and another mole of acetic acid. Question about that?
Do either of them get the oxygen?
Do either of them get the oxygen? The oxygen actually comes from water. So when you do the hydrolysis, what you'll see is one comes off as a carboxylic acid, and the water that's adding in the hydrolysis is what gives the OH to the other piece.
So does the oxygen just become oxygen gas or something?
No. One of them, so you need to look at the mechanism for this. But one of them comes off as a carboxylic acid. This comes off as the carboxylic acid OH. Water is adding to this part. That's where the OH comes from to make the other carboxylic acid.
Is whichever one comes first to a chain that's longer, or like alphabetically?
It's generally alphabetical, but again, no holds barred. No holds barred. If you name this anywhere near right, I'd be totally fine with it. You know what I mean? You're always given like 1 or 2 mistakes in nomenclature. We don't really, try and go down to quarter points. Okay. Yes.
So if this shows up in a cyclic molecule, is it sort of just the same?
Okay, cyclic molecules have different naming strategies, so we'll have to talk about those. That's a good question, though. We usually don't talk about them till the end, though. We stick with interconversions of intermolecules before we do intra. Okay. All right. We're going to skip over the ester for a minute because the ester is the hardest one. Here's my R group for the amide. Everybody sees my R group for the amide, right? So this is another butanoic acid. So I swap out that N everything for an OH. So that would be butanoic acid, right? So in this case, though, I have to account for these other carbons that are off the nitrogen off of here, right? This is how we always deal with carbons off the nitrogen. At the beginning, they're named as substituents. So this is N-ethyl, and then this would be butanoic acid, right? But it's not an oic acid. It's actually butan, so we drop that, amide, amide. Why? It's an amide. If it was an amine, it would be just an N. Very easy naming, okay? So this is N-ethyl butanamide. You don't need to denote the placement of the amide, and so is it carbon 1. Yeah?
Is there a space between butan and amide?
No, there should be no space, so I wouldn't put any space. So it's butan, and no space with the ethyl either. So this is all together when it's typed, right? N-ethyl butanamide, all together, all scrunched into one. Yeah?
What does the N stand for?
What's the what?
N stand for?
The N stands for I'm off the nitrogen. So if I had another substituent, say I had another ethyl group somewhere, right? If I had something else, I've just changed this molecule, right? This name no longer is a stand-in for what I have on the board. This guy here would be N2 diethyl butanamide, right? So it would allow me then to put an ethyl group back on the nitrogen and the second position, right? So N just says I'm off the nitrogen, not off a numbered carbon of the chain, okay? Nitrogen R groups are named in this fashion, as if they're substituents, okay? This is how it goes. Okay, the last one is the ester, and the ester just sort of defies logic. I can't explain to you where it's come from, but you can see the parent carboxylic acid, right? It's a 2-methyl propanoic acid. This O, though, R group off the O, is not named as a substituent, as we do with nitrogens. Not named as a substituent. It's actually named prior to the entire name. Okay? So we get something like this. This piece is named first, and then there's a space, and then I name this piece here. That's named second, right? This piece off the oxygen is named first, and then I put in a space, and I name the base R group, okay? So this would be named propyl, then a space to say I have 3 carbons off of the oxygen. The space comes, and then I say this is 2-methyl propan, dropping the oic acid. I had, I guess, O8. This is propanoate. Okay? So the O8s are esters. And you can see that they're named very differently than nitrogen substituents, and very differently than you would name ether linkages as well, which is very confusing. But I'm here to tell you this is the way that it goes. Okay? All right. I'm going to put some names on the board, and you're going to draw the structures in the right order, right? In the order of reactivity. Okay?
I thought it was L2.
Okay, which one of these is the most reactive?
D.
D. D is the most reactive. So I pull out the acyl chloride, it is the most reactive. So we're going to draw this out. We're going to draw out what parent carboxylic acids we get back, so we'll make sure that we can do that. We can see products of hydrolysis. We want to talk about what makes this most reactive. Maybe we can wait to the end and talk about them sort of in comparison. You should have some reason about what makes them more reactive.
I just wondering why we did most to least, most to least to most.
I don't know.
No.
No, no method of my madness. Yeah, absolutely none. Just decided to do it this way. Okay, so this is 4-methyl pentanoyl chloride. So I start always here with pentanoyl chloride. Pent says 5 carbons to me, so I draw out my 5 carbons. The OEO chloride tells me that I have a carbonyl at the end with a Cl. And now I look at anything before it to see if I have any substituents. I have the 4th position, a methyl, so I number out my chain and I put in my methyl group at the 4th position. So this is 4-methyl pentanoyl chloride. Yeah?
Is there spaces between pentanoyl and chloride and methyl?
There is a space between pentanoyl and chloride, yes.
Okay.
There is no space in here. It's different when it's typed and when I'm writing, just because the way I space my words when I write doesn't make it easy for nomenclature, though I totally agree. All right, so the base carboxylic acid is a swap out of this box entity for the Cl for the OH, right? So on hydrolysis, which requires no catalyst, so H2O alone, okay? H2O alone is going to give me back now my parent carboxylic acid, which I would name 4-methyl pentanoic acid, right? That's what its name would be, 4-methyl pentanoic acid. It's a swap out of the Cl for the OH. Okay? H2O alone. All right. Next most reactive, we did that one. What comes next? C, because it's the anhydride, right? And because I only have one name there, I know that it is a symmetric anhydride, right? If I had 2 names, I would know it's asymmetric, but it's symmetric. So in this case, I have something like this. This is benzoic anhydride. And I know that when push comes to shove on hydrolysis, which requires no catalyst, right? H2O alone will do it. I'm going to get back 2 moles of benzoic acid. Okay? 2 moles of benzoic acid. Everyone with me? Next most reactive, because that is my ester, right? Working down the chart. My ester is next. So I have to start over here, right? This is going to be my base parent. My base parent is going to be a hexanoate. So I'm drawing out 6 carbons, hex for the 6. Anoate tells me it's an ester, so it tells me on my terminal carbon, one of them, I have to have my double bond to my oxygen and an O. Now I question what's on the other side of that O, because I know it's OR. And And I have to go all the way to the beginning of the name to see what that is. So I come all the way prior to the space, and I see that's an isopropyl. Okay? So I'm going to add that on just because I'm thinking right now, oh, what's out here? So here's my isopropyl. Okay? But I've got to make sure there's no substituents, right? Because I've taken care of this hexanoate piece, and I've taken care of this isopropyl, but I see that I still need to put an ethyl group on carbon 3. So I come back over, numbering 1 always for the carbonyl carbon, 3 would be right there, and I'm sticking an ethyl group on carbon 3, and I've taken care of the whole name. Okay? So my base carboxylic acid is this piece here, where the OR group is replaced with an OH. So my base carboxylic acid is 3-ethyl hexanoic acid. 3-ethyl hexanoic acid. Now, this hydrolysis here requires a catalyst. Okay? Requires a catalyst. There's 2 ways I can run this. Okay? So, I'm going to put a little asterisk here. There's 2 ways I can run these with a little asterisk. Methodology 1 is to say, I'm going to take H2O and add H2SO4 or H3PO4 or some aqueous acid. That's method number 1. This is an acid catalyst. This actually is the opposite of Fischer esterification. It's the reverse of Fischer esterification. Acid catalyzed hydration of an ester is the reverse of Fischer esterification. Okay? The other way that I can do this, methodology 2, is to run this in a base and water. This is what I would say generally is called base-promoted hydrolysis. Nothing can be that entertaining on that phone, because if it is, I want to know what it is. It's got to be something good. I'm curious, because this is boring to me too. You're not the only one. This is generally base-promoted hydrolysis. Okay? They are named differently because it's the way the water is used or the catalyst is used is different. Acid catalyzed means that the acid is regenerated. Base promoted means the OH minus is being used up. Everyone understand the difference in language? This is a great theoretical question on an exam. What's the difference between acid catalyzed, when the acid is the catalyst, it's regenerated. This is base promoted, meaning I use up OH minus. It's literally can be a limiting reactant in my reaction, okay, being used. All right, different mechanisms. I can use either one of those conditions to hydrolyze my ester. I cannot use just water. If you add in just water, you are not really getting any reaction to happen. Okay? Does everyone understand what I mean? Because we've turned the tables between the anhydride and the ester. All right? So either A or E can be representations of the 4th priority here, right? Either A or E. I'm going to choose one of them to do, but I'll draw up the structure of E. We'll just put A over here. This is butenamide. So butene at the E, meaning there's a double bond, is at the 3rd position. So I start with butene, or bute 4 carbons. The amide tells me I have a double bond on that terminal carbon with a nitrogen. I want to know what's off that nitrogen. Okay? So I come to the substituents before, and I see there are no R groups or substituents off the nitrogen, which in essence means this is an H2. Unless there's N something in front, I assume there are hydrogens there. Okay? So at this point, I've taken care of my bute, I've taken care of my amide. I need to put in my 3-ene, right? So I have to go to the 3rd position and stick in an ene. So I have a double bond there. Okay? And lastly, So I took care of that. I got to deal with any substituents. So it says off the 2 positions, I have 2 methyl groups. So this is my amide that I have. This is the piece that's going to give me back my base carboxylic acid, right? So I can draw that out. My carboxylic acid would swap out that N, whatever's here, for an OH. This whole thing would be swapped out for the OH, okay? And I know this also is not very reactive and requires a catalyst, an acid catalyst or a base promotion, okay? Same concept. Okay? All right. Just to make sure that you can get E right, this says NN4 trimethylhexfluorinamide. So I'm going to go to my end and I see hex. That's where I start, hex. So I'm at 6 carbons. I have an amide, so I take my terminal carbon and make it the C double bond O with an N. I say, is anything off that nitrogen? Come to the beginning, and I see 2 N's, which means there are no hydrogens on here. If I saw 1 N, there would be a hydrogen and an R. If I see 2 N's, they're both R groups. They both happen to be methyls. So I'm going to stick those on there. And I see I also have 1 at the 4 position. So there's a methyl here. And I go back and check my name and make sure I'm not missing anything. I got the NN4 trimethyl, that's all taken care of. I have 6 carbons. Oh, here, I forgot this. The 4-ene. Okay? So I have to count out here and put my ene, my alkene in there. Okay?
Do we need E and Z in this?
You could do E and Z if you wanted, yes. They're not in these names, but absolutely you could. Yes. Or a what? Yeah, A and E are generally the same reactivity. I mean, there are small differences, but not ones that we're going to be talking about here this term. I mean, it's pretty obvious that they're not exactly the same, so they can't be, right? Okay, so we have most reactive to least reactive left. Sorry.
You're fine. When you're naming the carboxylic acid,
Yeah.
from the, is it enoic acid?
So it'd be enoic acid, yes. So this would be, that guy down there would be 2,2-dimethyl but-3-ene oic acid. Yes, the ene has to be in there, absolutely. Okay. All right, so in terms of why the reactivity order is this way, what can you give me? Yeah. Great. Leaving group propensity is one big argument here. The Cl is going to be our best leaving group. As I come down, you can see that the leaving group propensity is decreasing. Meaning they're less likely to serve as leaving groups as I go from most reactive to least reactive. Cl comes from HCl, pKa -7, leaving group. Acetate, that's a kind of the one you've memorized, the carboxylates, right? pKa of the conjugate acid 5. OR, pKa of the conjugate acid 16, right? It would come from an alcohol. NH2 minus, right? pKa ammonia, or conjugate acid ammonia, pKa 36. So yes, we definitely have leaving group propensity decreasing as we come down. That's number 1, and that's something we are going to account for, and that should absolutely explain to us why we're going to start needing something to make it go, right? We need to sort of start making the leaving group a better leaving group, doing something that will help that situation out, which is exactly why there's a turning of the tides, okay? What else can you tell me? Yeah.
Resonance.
There's a difference in resonance, absolutely, okay? You look at the resonance structures of each one of these, what it will lead you to is this. This electrophilic center here, labeled carbon 1 and the acyl chloride, is the best electrophile of the bunch, okay? Resonance is going to tell me that, because if I compare just the first and the last, that's all I'm going to do, the first and the last, and look at their resonance structures, okay? So I'm going to draw out, I'm going to go to an R, I hope that's okay. But if I look at this guy and its resonance buddy, which is this one here, okay, that's the acyl chloride, that's the resonance hybrid. Sort of try and make a guesstimate based on what I see. Okay? So I look at the first guy, neutrals should always contribute more. So I'm definitely going to be jacking up that number, right? They're all, column A in each case is going to contribute a lot more. But now I look at column B, and I say, this puts a positive charge on a Cl, negative charge on the oxygen. This isn't necessary. It's not like Cl's rescuing anything, right? It's just willy-nilly taking something neutral and now making, right, itself positive. Would do it if it were rescuing. It's not likely to do it when it's not, because Cl is electronegative, right? But if I look down here with the nitrogen, nitrogen's far less electronegative, right? Far less electronegative. So if I were to start putting numbers to this, and you don't have to come up with these exact numbers, but you should come up with a higher proportion of B contributing here than you would here. So maybe I'd be at like 97%, 3%, and here maybe I'd be at 90%, 10%. Again, you don't need to come up with the numbers, but you should agree that column B for the amide is going to contribute a little bit more because that nitrogen is less electronegative and hence willing to hold that positive charge, more willing than the Cl. Now, if you don't believe this, we can go all the way back to sort of week 2 here. In fact, that would be that way for us, right? All the way back to week 2 when we were sitting here discussing IR. And we had a big discussion, right, about the carbonyl bond strength. Go look up the carbonyl bond strength for each one of these. You're going to find it sits further to the right here and furthest to the left over here. And the reason for that is because this carbon double bond, carbon-oxygen double bond, has more double bond character because the resonance contributes less than the amide. Go back in your notes. You should come full circle here. The point being that this carbonyl is most electropositive, meaning it's a good electrophile, a weakening electrophile as I come down, and the weakest electrophile. Okay? So that is also something that we should see here as we move forward. Okay? We're going to start next class with just the 2 mechanisms very briefly, and we're going to move on to workshops. We'll work on that, and we'll work through that on Friday as well.